Hello, friends. I'm Dr. Sonali Tamhankar, and welcome to AI for the Grounded. N is for Neurosymbolic AI. With it, we enter the second half of our AI A to Z course. We start today with a book written by Nobel laureate Daniel Kahneman, Thinking Fast and Slow. This is a landmark book in behavioral psychology published in 2011. It talks about two kinds of thinking. System one, or fast thinking, which is almost effortless and instantaneous. System two, or slow thinking, is deliberate, effortful. System one thinking is intuitive, emotional, stereotypical. For example, when you detect anger in someone's voice or answering what is 2 plus 2. System two thinking is logical, calculating, conscious. For example, multiplying 17 by 24 or parking a car in a tight space. The two systems work like yin and yang. Let's revisit the Stroop effect we talked about yesterday. Tell me which color this word is written in. Blue, right? And this one? Green. Okay, now ready? How about this one? The first couple of times we answer instantaneously using system one thinking. Reading familiar words like blue and green doesn't take effort. We usually take much longer to respond on the last one because the two systems are fighting. You instantly read the word blue, but have to use system two to do a logical override and answer green because the word is written in green. So system one is incredibly efficient, but system two is in charge of logical thinking. Neural networks have often been compared to system one, a drawback being large generative neural networks can hallucinate. Symbolic reasoning can be used to ground them and acts like system two thinking. So we already talked about one such example, knowledge graphs. Especially in a field like healthcare, we want evidence based, precise information. Knowledge graphs are a structure that can hold such information. They have entities and relationships between them. Diabetes is treated by metformin. Combining LLMs with more absolute information that can be stored in knowledge graphs is an example of neurosymbolic AI. The firm logical skeleton provided by structures like knowledge graphs can help reduce hallucinations. So check out the AI for the connected case for knowledge graphs video for more details. Okay, let's look now at a few more examples of neurosymbolic AI, focusing on different ways in which the neural and the symbolic pieces can be combined. So we could let each of the two parts do what they are best at. So if we ask an LLM to do a 5-digit multiplication, it may recognize this as a math problem and write and execute a Python code to get the correct answer. So here we can use tools like Toolformer. I'll link a description. I'll link a reference in the description below. So this can be considered a form of neurosymbolic AI when it is combining the neural part, the LLM, with the tools which are manipulating symbols like Python. Okay, next, let's consider a driving application. So a neural network might recognize a stop sign and it might invoke a rule that if you see a stop sign, then come to a complete stop before proceeding. Okay, so having this strict symbolic part ensures legal compliance, even though the training data might have seen lots of drivers doing a rolling stop or a California stop. But okay, so before we trigger such an absolute rule, we want to be confident that we actually saw a stop sign. Right? So there is a concept of contrastive learning that can be used to increase confidence in a sense in a neural network prediction by increasing the contrast between the correct answer and the next best guess. So let's say we want to recognize a digit to be a 1 or a 7. Consider two models, A and B. So both characterize the images correctly, But model A characterizes the image to be the first image to be a 1 with probability zero point 0.6 and to be a 7 with probability zero point 0.4. But zero point 0.6 is greater than zero point 0.4. So the prediction is 1, which is correct. And the second prediction is also correct. So it does answer correctly, but not with a very high margin. Now, model B characterizes the first image to be a 1 with a probability of zero point 0.9 and the the first image to be a 7 only with a probability of 0.1. So this is also correct both times and with a much higher margin between its guesses. So both models are correct, but we can intuitively see that model B might be better. So model A is just thinking, okay, this is a 1. Model B is thinking, this is a 1, not a 7. So the contrastive learning is a method that trains AI to think more like model B rather than model A using what's called margin maximization. So this is a concept similar to SVM or support vector machines, where you try to push the correct and the incorrect answers as far apart as possible. Okay, so another technique is called energy-based methods. So these take inspiration from physics, particularly the concept of lowest energy state or ground state, like a ball settling in the lowest valley. So you don't need to understand the math here, just keep the picture of hills and valleys in your mind. Okay, so let's consider the problem of recognizing such digits, but imagine now that these digits are part of a Sudoku. Okay, so looking at one particular spot, this a neural network might recognize the image to be a 1 rather than a 7 because this is the lower valley, this is the lowest valley, so that is its prediction that the image is a 1. Okay, but now let's introduce the symbolic part, rule based piece. So let's say there is already a 1 in the row. So the symbolic piece would say that, hey, there is a 1 in the row. And the way the energy-based methods handle this is that they create this hill at 1. And then they push the ball down to 7. So this becomes our new prediction. So the energy-based models, these are one way to incorporate these symbolic constraints into your predictions. Okay, our final example today is Alphafold. This is a spectacularly successful protein folding model. The neural network predicts geometric relationships, distances between residues and orientations as well. The distances must satisfy a rule, the triangle inequality. So if a neural network says that the distance between some A and B is 1 in some units, and the distance between B and C is also 1, but it says that the distance between A and C is 4, this is impossible, right? There is no physical arrangement of these points A, B, C that can match these distances because they violate the triangle inequality. A and C can be at most 1 plus 1 or 2 units apart in this situation. So incorporating this symbolic part can help ground the protein structure using basic geometry. So the way Alphafold handles this is highly sophisticated, using something called triangle multiplicative update and triangle self-attention. So this is neurosymbolic AI through what is called geometric inductive bias, teaching the models to prefer solutions that satisfy spatial constraints like symmetry or triangle inequality. So note both the neuro and the symbolic part, the system 1 and the system 2 thinking, they're both important. They're like yin and yang. Like in our stop sign example, we needed the symbolic piece because we needed that hard rule to make absolutely sure that the car stops fully when required, because that's the law. But we also absolutely needed the neural network piece, because there's no way to write a rule that specifies what combination of pixels is a stop sign, right? So you need neural networks. That's the only real practical viable image recognition option at that scale. So that is why many people believe that neurosymbolic AI is the most promising path to building effective and reliable AI systems. Okay, so we barely scratched the surface of this topic today. I include references below for more rigorous follow up. So, quick recap, neural and symbolic parts of AI are like System 1 and System 2 thinking. Building AI, combining both pieces, is an art and science. So this really is involved. So like if you just got the concepts today, but feel a little uncomfortable in details, that's not you. It is quite complicated to mix these things. And the references below and the math and the code is the only real way to get at this. And the frontier of AI is converging on neurosymbolic architectures. So that's it for today. Tomorrow, our topic is overfitting, which involves giraffes and grokking. So don't miss it. See you tomorrow. Bye.